reproducible AI infrastructure. So why I cannot, 1 second, no. Okay, so here I'm showing you a bit more detail on the standards that Anna described. So we put a lot of emphasis on this because basically documenting the models is one of the very, very, very key aspects of the zoo for the rest to work, right? So we need some sort of specifications to build upon. So basically, these standards, they are included in what we call the resource description file, and they contain information about the model, as Anna said, how are the tiles and how, what is the input and output shape. So then when we process very large files, usually, you know, we have to do this kind of tiling. We can then in the user-friendly tools reproduce it, and then there is some information about the biological samples that are being analyzed with these models. So here, this I hope it's clear. What we mean is very, very basically, and say it very broadly, we have a text file, right, that contains fields, and all these specifications are very, very, very explicitly written. And the very good thing of having these kind of standards, this is our format, is that we can consume with Python or Java code, and this means that we can start building the connections with all these user-friendly tools. So Finn will tell you more about how we consume this, so I just wanted to emphasize this aspect because then the rest kind of makes sense. So one of the questions when we go into the use of these models is how can we use these models with our data? This is the most recurrent question that we have when we present the zoo, and where we have to retrain it most of the time. And thanks to those standards that we mentioned, and thanks to the very, very big Python ecosystem that Finn developed, that he will introduce it later, we are able to consume with the softwares that we are also developing in parallel. So we have Zero Cost, BioPy, Ceramics, Deep Learning for Mic everywhere. There are tools more devoted to the training that they build a connection with the zoo by consuming these standards, but being able to load the models or to then export them. And that's how we kind of get synchronized with the zoo. And these are community partners as well. So what I'm going to present today is more deep learning for Mic everywhere, because we go more into the reproducibility part of the zoo. So as well as when you do experiments, when we work with computational environments, we have a very, very big issue on reproducibility. So basically, we develop our code in let's say, in Linux or in Mac. And then when somebody wants to try it, well, they have huge issues with all these dependencies behind deep learning algorithms. So what we want to target is, of course, we want to be able to be reproducible. So basically we develop a code, or somebody develops a code, and then a new person is able to use it. So we give all this kind of environment and they can reproduce it. But this has to also be stable in the long term, because if we think about the timings that we have in biological research or life sciences research, we speak about years. And while computational tools, they are updated every 6 months or whatever, this doesn't happen when we do research, right? So in this context, one of the solutions, and this is not new from us, is to use virtual machines. And one of the most common tool for virtualizing machines is Docker containers. So very simply, we have kind of like a box in our, we built a box, a container, right, that has all these very specific dependencies with their versions, and then we are able to distribute these boxes across the systems and build these kind of virtual machines, no matter the operating system that we have. This is, we use for these Docker containers. And I mean, they work very well, but sometimes it's complex to build them. We need to write a recipe that explicitly tells all the dependencies and all the requirements that we need in this virtual machine. Then Docker kind of builds an image. And then from this image, we can create as many containers as we want. And here, I mean, if this is a bit complex, what we did was to write a post in Focaplane where we very, very detailed explain for non-expert users how is this containerization working and why it is important. So I would recommend you reading this. So in deep learning for Mic everywhere, what we did was first to build the functionality to do the containerization, because although it sounds like a very simple process, we really need to be very picky with all the details that we put there. So once we are able to virtualize in these virtual machines the entire algorithm with let's say the training functionalities and whatnot, this container is uploaded to Docker Hub. This is a repository where all these kind of virtual machines, let's say, are stored in the cloud, and they will stay there in the future. So to do this, we built a continuous integration that basically is like a code in GitHub, let's say, right, that will check that the format of the algorithm is correct, that the Docker image can build correctly, and that this container that we build with all the requirements is compatible in Mac, Windows, and Linux. And once this is fulfilled, we will upload the image, the virtual machine, let's say, to Docker Hub, but we also connect directly with the SU. So if there is a new algorithm coming that is not us, it will be as a notebook, it will be also published in the SU. So here is where the specs come in again. Because to build this connection, we really need to follow the format from the SU. So of course, that format that I explained you before was for models, but we are trying to build now formats also for these datasets, for these notebooks, and now for the containerization system. So with this, then what deep learning for Make Everywhere does for non-expert users is once you launch the interface, it will download the specific virtual machine that you need for your very specific operating system. It will run the installation of the Docker container, and it will launch directly the user-friendly notebook for you to start training your models or to start doing the inference locally. So this is basically the interface. You double click on the executable that we built. You will choose one notebook from the collection that we have available, and it will automatically open the notebook in your browser. And the cool thing of this is, because we are building these virtualizations, these kind of containers that they are closed and you can launch them whatever you want, it means that the same notebook with exactly the same dependencies can run not only on your laptop, but you can also use it in any GPU service of your institute, or if you have another computer with a GPU. So basically, we start building upon cross-platform compatibility systems. Here, again, we, of course, offer all the zero-cost notebooks. We offer some example notebooks for interacting with the bioimage model too. But of course, you may want to have your notebooks and all your algorithm in your GitHub repository and still use the containerization part of the functionality of building the container, making sure that everything works and having it in the long term. Reproducibility kind of ecosystem, so you can always push only the specs, so you can build a connection with deep learning for Make Everywhere, and then although your code and all your development will be in your GitHub repository, with this you can automatically ensure that the Docker container will be in the cloud and that your notebook will be in the bioimage model. So I think I have 1 minute. So because we are speaking about a scalable also AI, I will very briefly go into why this containerization is important, not only for you, but also how it will become important for the infrastructure of the bioimage models. So we have the website, and the website is empowered by what we call the bioengine. And this is a very complex system that what allows is basically for you to be able to run these models in the browser, as Anna was showing to you. So basically, when you decide to test one model, this is connected to some server that is somewhere else that we are provided with GPUs, and you can run these models without using that computational power, right? And this is a work from Niels and Wei specifically. So they built a very, very complex system based on the Haifa server. That's the very cool, I would say, feature of this whole system is that the server allows the connection with their high performance computing service, right? And here they use Kubernetes to organize the jobs, and they will use here, of course, they use the Docker containers, and this is connected to the storage from the SU. So it means is that you from the website can connect to this server and use this system, and many other people can do it as well, right? But you don't interfere with them, and there's no like a data transfer or anything. This is all kind of managed by the bioengine. And of course, a web client can be a person, but it can also be different softwares, or it can be different institutions. So with this, I would like to thank the entire AI4Life team that is actually huge, I would say, and also the lab where I'm doing my postdoc, Ricardo Enrique's lab, where we develop all these tools.